Okay, let's start with lecture 8. Today we are going to talk about spherical coordinates. These are is similar to the polar coordinate and the cylindrical coordinates, which are used to evaluate certain double integral or triple integral with certain symmetries. So first, let's get some geometrical idea of the spherical coordinate. So suppose you have XYZ coordinate system, and you have a sphere, unit sphere, and suppose you have points on the sphere. Let me take this one, and then there are some geometrical quantity related to this point. First, let's connect this point A with the origin O, and also we do projection project down to xy plane. You have a point, let's call it A prime. Okay, also you connect OA prime. Then for vector OA, for vectors OA and OA prime, we can use polar coordinates to parameterize them. Of course, here polar coordinates are a little bit different from the usual one we learned before, and I will tell you in detail. So first, for OA prime, then you see the angle is given by this one. So let's call it theta. So what is theta? Theta is the angle between OA prime and the positive x-axis. Okay, then the vector OA prime, so can be OA prime can be write down as the length of OA times cosine theta, and the length of OA times sine theta. Okay, now let's analysis OA. Now turn to OA. So here, instead of project to xz, yz, or xy plane, we consider the plane determined by z-axis and OA. In other words, now we are considering this plane. So let me use this one. Do I have more choice? Okay. Never mind. We are considering this plane. You can extend. Okay, then in this plane, what is your angle? Your angle is here, so let's call it phi. So we have phi is the angle between OA and the positive z direction. Okay, then the vector OA is given by length of OA times here in this case actually tautologically we also have z coordinates, so I write here you have 0, and for OA case it's a little bit more complicated because now you are not only rotating xy plane to some screw planes, but also you have some asymmetry between the axes. Okay, so instead of just write down this, we set up some equations, because this way you can derive similar to in a similar way to this, but then a little bit complicated by a geometric argument. Whenever you had difficulty in using geometry, you turn back to the equation. Okay, then what do we have? We set up carefully. So suppose A has coordinates x, y, z, and coordinates. So here we assume the length of OA is rho, is the third parameter. So totally you have one parameter here, theta, phi, and rho. Therefore, you expect to have a solution for x, y, z in terms of rho, theta, phi. Okay, now so what equation you have? First, let's compute what is cosine phi. What is cosine phi here? So recall what is phi. Phi is this guy or this one. So cosine phi just OA dot K is the positive z direction divided by length of K and the length of OA. And here, what is the coordinates for OA is x, y, z, and the K is 0, 0, 1. And in the denominator, you have length of K is 1, length of OA is this one. Okay, so finally you have cosine phi is z over square root x squared plus y squared plus z squared. Okay, now what is rho? Rho is easy because by definition, rho is the length of vector OA. So you have square root x squared plus y squared plus z squared. And then what is theta? What is cosine theta? Okay, so here cosine theta is the angle between A prime and x, and what is the coordinate for A prime? It's x, y, 0. Therefore, cosine theta, just by the geometry in 2D, is x divided by x squared plus y squared, and correspondingly, you may have sine theta is y over square root x squared plus y squared. Okay, this is the formula for rho, theta, and phi in terms of x, y, z. And if we resolve it, we can represent x, y, z in terms of rho, theta, phi. So for example, we first have what is z? So here, look, z is here, and if you plug in, so z is square root x squared plus y squared plus z squared times cosine phi, and you plug in this one, you have z is rho cosine phi. Okay, and now, so this is one equation we need, and then rho squared equals x squared plus y squared plus z squared, and if we plug in the formula for z, we have this one, and then what do we have? We have x squared plus y squared equals rho squared sine phi squared, and or x squared plus y squared square root equals rho sine phi. Yeah, I should mark here. It's a little bit tricky because literally you should have positive and negative, but here we only have this one y, actually because we restrict our phi is between 0 and pi. Okay, next, by this formula, then you can plug into the third equation. Then what do you have? You have x is square root x squared plus y squared times cosine theta, and then you have rho sine phi cosine theta, and correspondingly, if you plug into this one, then you have rho is y is square root x squared plus y squared times sine theta, which is rho sine phi sine theta. Okay, so as told, we have the following. X is rho sine phi cosine theta, y is rho sine phi sine theta, z is rho cosine phi. But then, of course, this formula just gives you the relation, doesn't give you the domain for rho theta phi. You have many ways to derive the domain, and one geometrical way is look at the angle phi and the theta. So the angle theta can rotate all the way around the z-axis on xy plane. So the region is from 0 to 2 pi, but the phi can only go from the positive direction to negative direction. So phi is between 0 to pi. And similar to the polar coordinates, rho, of course, the only constraint is rho is positive. Okay, therefore here you have some natural domain for the variables rho, phi, theta. Phi is between 0 and pi. Theta is between 0 and 2 pi. Okay, so this is the spherical coordinates we are going to use in the following. Now let's look at some example to get familiar with the polar coordinates. So first example, compute the coordinates of the point rho theta phi equals 2 pi over 4 pi over 3 in x, y, z coordinate system. Solution. This is pretty straightforward because we have the formula in a very clean way. Sine phi, sine theta, z is rho cosine phi. Okay, then you plug in. You have x, y, z equals 2 times sine pi over 3, sine pi over 3, cosine pi over 3, and then cosine pi over 4, sine pi over 4. So this is 2 times square 3 over 2 times square 2 over 2. This is 2 square 6 over 2. And similarly for the y coordinates, you have square 6 over 2 as well. And then for z coordinates, you have 2 times 1/2, which is 1. Pretty straightforward. And next, we do the inverse transformation. Suppose x, y, z coordinate is given by 0, 2 square 3, negative 2. And what is rho theta phi coordinate? This is a little bit more involved because the formula for rho theta phi in terms of x, y, z are not that straightforward. So rho is given by square root of sum of squares. So you have 2 square 3 square plus negative 2 square. So totally you have square root 16, which is 4. And then theta, we only know cosine theta is x divided by x squared plus y squared. Sine theta is y divided by x squared plus y squared. So for this one, cosine theta is, because x is 0, no matter what it is 0. And then for y is negative 2. And then in the bottom you have you have 2 square 3, this is y, divided by 2 square 3 square, so it's 1. And then if you draw the picture, the point corresponding to cosine theta is 0, sine theta is 1, is this point with coordinate 0 and 1. Okay, so so this is in xy coordinates, and then the angle corresponding to it, angle theta just pi over 2. So here you have theta equals pi over 2. Okay, then for cosine phi, it's z over rho, and the z is -2, rho is 4, so -1/2. And recall, since phi is between 0 to pi, the only solution is phi equals 2 pi over 3. So you will have 2 pi over 3 go like this, and then this is 1, this is 2, but then cosine is negative, so here cosine theta is -1/2. And then this angle actually is 60 degrees or pi over 3, so totally theta will be 2 pi over 3. Okay, as a conclusion, rho theta phi correspond to the point is 4 pi over 2, 2 pi over 3. Actually, the same as in the polar coordinate. For this part, for theta part, usually you need to determine the domain, where the point is, which quadrant the point is. For example, it's better to look at the picture, because usually you have multiple solutions if you only look at cosine or sine. But for phi, since we are in this region, usually you only have one solution, so you don't need to consider too much the geometry. Okay, next we will apply the spherical coordinate to calculate the triple integrals. So first, as what we did in polar coordinates and cylindrical coordinates, you need to figure out the transformation law, and the key point is you have an actual factor. So how to determine the actual factor, what it is in this case. So what is the actual factor in the transformation law? Actually, I will give you two methods to calculate the actual factor. First one is a geometrical way, just approximate a tiny cuboid, so a tiny region by a cuboid, and then we derive it. And second method is by calculator Jacobian, which I will give you at the end of this lecture. So suppose the region we have in rho theta phi coordinate is given by some cuboid, but then in xyz coordinates, the rectangular coordinates, you have a little bit more complicated. region. Okay, and yeah, you have this one, so let me fill in. Okay, and suppose this region is small, then what do you have? Then this angle is, so let's do projection first. Project down. So you have red one here, project down. Okay, so this angle is delta theta. And then this angle is delta phi. And then this part is the difference of the radius, so it's delta rho. Now let's calculate the volume of the yellow part. Although it's curved, we can view it as a cuboid approximately, and then we need to figure out the length of its three adjacent sides. So for example, now we already know this part is delta rho, and then what is the green part? So length of green side, what is this? And you see, you just restrict to 2D. Look at the look at this fan. So the angle is delta phi. So what's the length of this side? Of course, you need times the length of this side. So what is the length of this? This just rho, right? Therefore, the green side has length rho times d phi. And then let's figure out the length of the red side. So this is a little bit more involved because now you have this one, Okay. Let me think about. Theta. Okay, so this red side, I see. So the red side is same as the length of this part. Okay, then if you look at this part, so the length is the length of this side times delta theta. So let me call it rho prime. So it will be rho prime times d theta. Okay, but then the rho prime is a projection of rho. Therefore, you will further have rho times sine theta, which is rho prime times, sine phi times delta theta. So why rho prime equals rho sine phi? This is because if you only look at the actual point and its projection, then you will have the following picture. So this is rho prime. And then of course, then here rho prime will be the angle they call alpha, cosine alpha times rho. But what is alpha? So since this is theta, this angle is phi. So alpha is pi over 2 minus phi. Therefore, you can derive the following. Okay, so if you combine everything, then the volume of the yellow part is given by length of green side times length of red side and times length of blue side approximately. Okay, and then you plug in the formula. You have rho delta phi times rho sine phi delta theta times delta rho, which is rho squared sine phi delta rho delta theta delta phi. Therefore, for the cuboid domain in rho theta phi coordinate, you can write down the integral as following. So theta, so this is in XYZ coordinate system. Okay, then we calculate in spherical coordinate system. And since the domain E is given by this for simplicity, okay, then we can write as following. The integration from C to D, this is for phi, and then from alpha to beta, this is for theta. From A to B, this is for rho. And inside you have F, use substitution for X, rho sine phi cosine theta, rho sine phi sine theta, rho cosine theta, and times rho square sine phi d rho d theta d phi. So this is the transformation law we are going to use. And here, most importantly, you have actual factor rho square sine phi. Yeah, I will first give you some applications, then at the end I will give you another way to calculate without using too much geometry. Actually, we don't use any geometry for that method. Okay, and in reality, sometimes we want to consider a little bit more general domain than cuboid in spherical coordinate system. So for example, we might interest in the type 1 domain. You change the range for rho to be bounded by two functions of theta and phi. Okay, then for the following example, we can calculate easily. I will not write down the formula for type 1 domain. We will show that by next examples. So first, let's look at one easy case. Suppose we have a unit ball. And how to evaluate this. So without using spherical coordinates, then you had a hard time to evaluate this because you don't know how to evaluate exponential some square root function of z at the first step. Okay, then you get stuck. But now, if we use spherical coordinates, then everything is easy because you will see you won't have square root as your index. So first, let's write B as cuboid in spherical coordinate. So rho, of course, is between 0 and 1, and theta has a natural domain 0 to 2 pi. Phi is naturally bounded by 0 and pi. And then I is given by, first you integrate phi if you want, and then theta, and then inside you have rho. Of course, you can change the order because here you can project in any order. those limit points just constant functions. Okay, then you have exponential plug in. So the exponential actually is rho squared 2/3, 3/2, and then you have actual factor rho squared sine phi and d rho. Okay, and then you simplify it. E rho cube rho squared sine phi d rho. So for this one, actually you can use chain rule. Therefore you have E rho cube divided by 3, 1, 2, 0, and the sine phi. And then you will have E over 3 minus one over 3 sine phi. And since this is a constant function with respect to z, with respect to theta, then you can integrate in the following way: sine phi times 2 pi. Okay, now you can further simplify it to calculate in as follows. Okay, then when you plug in pi, you have negative 1 minus negative 1. So totally you have 2 here. So e minus 1 over 3 times 4 pi. This is our answer. So next, let's look at type 1 domain case. So suppose we are using spherical coordinate to calculate the volume of the solid that lies above the cone z equals x squared plus y squared and below the sphere x squared plus y squared plus z squared equals z. First we need to draw a picture, and so for first step we need to change this a little bit into standard form so that we can locate the origin, the center of the sphere and the radius. So we complete squares. Z minus 1/2 square equals 1/2 square. Okay, then the sphere has center 0, 0, 1/2, and with radius 1/2. Therefore, it passing through the origin. Okay, next, let's draw the cone. So the cone, if you restrict to xz plane, for the cone, if we restrict it to the xz plane, in other words, you set y equals to 0. Then what do you have? Suppose you have x and z then you will have a curve like this. Okay, similar for the restriction to YZ plane. Therefore, the cone you will have is like this. And then by the definition, the solid we're interested in is below the green part and above the red part. Okay. Now let's denote this as E. This solid as E. Next, let's look at the region for E in terms of rho, theta, and phi. So first, let's transform the defining function of the blue part into rho, theta, phi. So what do you have? On left hand side you have rho squared, on right hand side you have rho cosine phi. Okay, therefore the boundary is rho equals cosine phi. And actually because this is rho equals 0, because it's inside the ball, and therefore inside blue part means rho is between rho 0 and cosine phi. This is first condition. Second condition for the cone, above the cone, so that means z should be above x squared plus square root x squared plus y squared, and rho cosine phi greater than or equal to rho sine phi. What does that mean? That means cosine phi is greater than or equal to sine phi. So also remember phi is between 0 and pi. So phi is between 0 and pi over 4. Okay, then for theta it's free. So E can be described by the following formula. Theta is from 0 to 2 pi, phi is from 0 to pi over 4, and the rho is from 0 to cosine phi. And then the volume then is given by integration of 1, and we transform into the polar coordinate. You will have the following. Use the formula here. And don't forget, you need to add extra factor rho squared sine phi. Okay, so first we need to integrate rho and recall the differences. Here, the upper limit of rho integral is depends on variable phi. Therefore, first step, you have this sine phi d phi d theta. Okay, then you have cosine phi cubed over 3 times sine phi d phi d theta. And then here you can use the chain rule. So cosine phi 2/4 divided by negative divided by 4 times 1/3 pi over 4 0 and 0 to 2 pi d theta. And then you plug in, you will have negative 1/√2 to the 4th divided by 12 minus 1/12 0 to 2 pi d theta. Then you have 1 minus 1/4 divided by 12 times 2 pi. So totally you will have 3 4 times 1/2 times 2 pi. You have 4 and then you have 2. So finally you have pi over 8. Okay, due to time, I will leave the transformation to next. Okay, since the transformation is related to a little bit related to the second midterm, so probably it's better to include it here. Okay, so as I promised at the beginning, second method to calculate the actual factor. And so next time we will discuss how we derive this type of formulas. But this time we will just take it for granted and then do the computation. So suppose x, y, z is related to a new coordinate system UVW by functions g, h, k, and we define the Jacobian and denote by partial xyz, partial UVW, defined by the following. Partial xyz, partial UVW. This is a determinant. Partial x, 3x3 matrix. Partial x, partial u, partial x, partial v, partial x, partial w. And then you change it to y. Partial y, partial u, partial y, partial v, partial y, partial w, partial z, partial u, partial z, partial v, partial z, partial w. Or so if you look at this, you keep x in each column, but then you can do the reverse way. You keep x in each row. So this is in each row, and then you can keep it in each column. X, partial u, partial x, partial v, partial x, partial w, partial y, partial u, partial y, partial v, partial y, partial w, partial z, partial u, partial z, partial v, partial z, partial w. Actually, if you later on, you will know this is transpose of the matrix. Okay, and then the geometrical meaning we will show next time. So suppose gamma, suppose x, y, z can be written down as a vector value function gamma of u, v, w. Then what we are calculating is the following volume of the cuboid. With a size gamma u, gamma v, and gamma w. So actually the Jacobian is volume of the yellow part. And if you use the formula we learned before, then it's gamma u cross gamma v dot gamma w. Okay, and if you expand that, you get the previous formula. We will explain in detail next time. Here we only want to derive the actual factor for polar coordinate. So x is rho sine phi cosine theta, y is rho sine phi sine theta, z is rho cosine phi. Okay, then what do you have? If we compute the Jacobian, rho phi theta, then we have, so first let's write down the formula. Partial y, partial rho, partial z, partial rho, partial x, partial phi, partial y, partial phi, partial theta, partial phi, partial z, partial phi, and then partial x, partial theta, partial y, partial theta, partial z, partial theta. Okay, then here you take x rho derivative of x, you have sine phi cosine theta. Then you have sine phi sine theta, cosine phi. And next, second row, you will have rho cosine phi cosine theta, rho cosine phi sine theta, and the negative rho sine phi. And last row, you will have negative rho sine phi sine theta, rho sine phi cosine theta, and then you have 0. Later on, if you learn something in linear algebra, you can expand the last row. But here, since we don't know that, we will expand the first row just as what we did for the cross product. So here you have sine phi cosine theta times rho cosine phi sine theta times 0 minus negative rho sine phi times rho sine phi cosine theta. So you combine this with this. Okay, similarly, for the second one, you have negative sine phi sine theta times rho cosine phi cosine theta times 0 minus negative rho sine phi times negative rho sine phi sine theta. And then lastly, you have cosine phi times rho cosine phi cosine theta rho sine phi sine cosine theta minus rho cosine phi sine theta times negative rho sine phi sine theta. Okay, now let's calculate. So sine phi cosine theta, and here it's 0, and then for this part you have rho square sine phi square cosine theta, and then minus, this is gone, and then minus plus, so you have plus sine phi sine theta rho square sine phi square sine theta, and then plus here you have cosine phi, inside you have rho square sine phi cosine phi cosine theta square plus rho square sine phi cosine phi sine theta square. Okay, now notice this, and we can get sine phi cosine phi. Also for first two, you can further combine the indices. You have rho square sine cube sine phi cube cosine square, and then second one you have rho square sine phi cube times sine square, and then for third one you have cosine phi rho square sine phi cosine phi. Also notice this and this, you will have rho square sine phi cube plus rho square sine phi cosine phi square. And if you rewrite this, if you factor out rho square sine phi, then you have sine phi square plus cosine phi square. Then it's rho square sine phi. That's exactly the indices we derived for the spherical coordinate, the extra factor we derived for that. Okay, I will stop here.